Is Jason Box. He's a research professor in glaciology at GEOS, Geological Survey of Denmark and Greenland in Copenhagen. Jason, he moved to Denmark in 2013, and by the way, he speaks Danish already, from the US. He's an experienced obtaining ground truth data for satellites and climate models from the surface of the Greenland ice sheet. Jason was a contributing author to the last two IPCC Working Group 1 assessment reports. Welcome, Jason. Yeah.
Thank you. I'll be speaking about a number of activities as part of the Arctic Monitoring Assessment Program, AMAP, which has a report coming out next year, Snow, Water, Ice, and Permafrost in the Arctic. That's an update. What new have we learned in cryosphere? Basically, the chapters I'm covering is about land ice. What new have we learned in the last 5 years? And I can tell you, after 350 citations, it's an impressive kind of, I would call it a kind of a tsunami of knowledge that's come out on land ice, and not just land ice, different elements of the Arctic climate system. So I'll just be talking about the land ice components, emphasizing my home away from home, Greenland, but as I've taken the challenge in helping write chapters about the pan-Arctic scale and seeing what land ice is doing across the Arctic, it's a powerful story that it tells. I also want to, thank Norden and Nordforsk for helping put on this event. This graphic is just one that would appear in the Swiper report, where we have multiple independent lines of evidence that show that the Arctic is undergoing a rather profound change. Summer air temperature increase of 2 degrees in the last 30 years. Permafrost temperature increase on that second line of about 2 degrees. The greening of the Arctic and the shrubification of the Arctic. The willows are growing higher, bushier, and the snow cover decline is the blue line below that. Arctic sea ice decline and the profound transformations that poses to animals and that subsist or that depend on the platform of sea ice. The energy, the changes of the energy exchanges because of the loss of the reflective cover of sea ice. And then the land ice at the bottom, I'll give more detail on here. Greenland is a fantastic laboratory to study climate change, as land ice both indicates change, but also has impacts that go outside of the Arctic. One of the impacts you hear a lot about with land ice is when you transfer this mass into the ocean, it of course raises sea level, but there's a few other impacts that include changes to the ocean circulation, some interaction with this cold blob that's been forming south of Iceland, and that has the potential, it appears, to affect the weather in northwestern Europe, in the Nordic regions. Changes in the nutrient export from glaciated systems, because runoff has increased, doubled in the last 50 years. Contaminant re-release, the so-called blast from the past. So there's these multiple impacts from changing land ice. I came to this problem from maintaining climate stations on the inland ice of Greenland. And Denmark has a complementary network of stations here indicated in red. And so we have 40 stations on Greenland ice that help us check climate models, satellite observations, and this is real ground truth because you know what's really happening, and to understand melt through an energy budget. One of the key outcomes, or what we realize, is really the interaction of land ice with the ocean. And here at the front of one of 200 wide glaciers discharging from Greenland, you see this dark-colored, sediment-rich plume of meltwater. And the exchange of heat energy with the ice front is key in the stability of these conduits through which ice flows into the sea. And these are actually very vigorously circulating, we call them like jacuzzis, that as the Arctic Ocean has been warming. This is in Baffin Bay, west of Greenland. Those lines, they go from earlier to later in time. And we observe a kind of 1 degree warming of the seawater temperature at about 500 meters below the surface. And that's right where a lot of the largest glaciers are grounded. So this actually packs a punch, this warming at depth below in the ocean. And this cartoon shows how that warm water at depth is entrained, drawn into a circulation up against the underwater ice cliff at the front of these large marine terminating glaciers. And that is a direct link, also driven by a feedback with the meltwater that runs through the system and drives that circulation. Water increasing at the surface on glaciers is hydrofracturing downward, because water is heavier than ice. And that's just one mechanism that can produce some very dramatic ice shelf disintegrations, like this one that happened in record warm weather in North Greenland. And it may be unnecessary to highlight that the climate system is being perturbed in an abrupt sense on the kind of time, on a long time scales of this, but this near kind of vertical climb in greenhouse gas, that has the profound impacts on climate that brings us here to these meetings to try to manage the fact that human activity has become a force of nature on Earth. Here's a summer temperature reconstruction the last 2,000 years of Arctic summer temperatures. And then at the period of industrialization, temperatures rise abruptly. So when you look at climate change on a longer time scale, you see that it's abrupt in nature, and the Arctic land ice helps indicate that change. So that's the past 2,000 years, and what I'll show you in the next slide is the next 100 years put onto this graphic. We have essentially the Paris Accord. If it's successful, you get the Arctic summer warming of almost 3 degrees. That seems to be our best case scenario, and already the Arctic is undergoing a major transformation. There is a significant difference with the business as usual scenario way up at the top there. That difference will be played out in the rates of sea level rise and climate disruption later in the century. But this change is already underway, and the global warming is concentrated in the Arctic because of the loss of a reflective cover of snow and ice, also because of increased heat transport and the changing thermal structure of the atmosphere in the Arctic. So this is kind of an early warning location, and those impacts, as Lars Otto showed earlier, are felt outside of the Arctic as well. The SWIPA report from AMAP published this sea level reconstruction that goes back 2,000 years, and you see the sea level rising 20 centimeters in the medieval warm period, sea level dropping into the Little Ice Age, and then taking off again, well, the observations go until the dark blue bar there, and then it's the certainty of sea level, mid-century, end of century, what you see on the far right of that graph is, of course, the subject of a lot of work. You can see these three different estimates over time reflecting we don't have a good handle on just how fast sea level can rise. But this is kind of a teaser for the AMAP SWIPA 2017 report, where we revised this. Because given the new information that's come out in the last 5 years, we can make a more credible treatment of this, really what the Arctic land ice role is in global sea level. And that's what I'm going to talk about in the following. Really, for the first time in the last 5 years, we now have a globally complete inventory of land ice contribution. The inventory of land ice contribution to sea level has been reconciled among multiple independent techniques and found to be consistent. And on the global scale, in this period of 2004 to 10, when we have a very high quality satellite measurements, it's the Greenland ice sheet, which is the largest single source of global sea level change from water being added to the ocean, followed by the West Antarctic ice sheet. If you go all the way around that pie chart, it's actually the East Antarctic ice sheet which is gaining mass, that kind of keeps Antarctica out of play relative to Greenland, because after all, Antarctica has about 9 times the volume of ice than Greenland. But West Antarctica, the green slice there at the bottom may grow, but we don't have a good handle on that. You can't really talk about sea level without mentioning Antarctica. I just want to show this table, not to refer to each number, but we have finally a complete inventory, again, of the sea level contributions, to rank the relative importance of these again. And then it's really the bottom line that I want to draw your attention to, that the Arctic, when you add Greenland and the Pan-Arctic glaciers, the Arctic is the source of 7/10 of global sea level rise from land ice contributions, 70%, and that's shown more simply here. The Arctic is dominating sea level rise at the present time. It seems likely that Antarctica will take over from that. But that won't be that the Arctic ice would slow down. It's just that Antarctica starts to kick in. The area of the different peripheral ice, so this does not include Greenland, but it includes the smaller ice bodies around the Arctic. And so Arctic Canada in the north is a quarter of that glacier area. Arctic Canada in the south, that's the purple area on the left. Arctic Canada is a little bit upstaged by Greenland, but it's kind of punching above its weight because the Canadian Arctic glaciers are melting faster than the Greenland glaciers are, because they're lower in elevation. They're affected by the same weather systems that have been affecting Greenland as well, and those glaciers in Canada, then Alaska, Russian Arctic, they add up to the fact that within the Arctic, Greenland is balanced by the contribution from so-called small glaciers. We actually have, I would say, quite a nice inventory of surveys of glacier mass balance. These are so smaller glaciers like Stor Glacier in Sweden and glaciers in Iceland and so on. And so from 1971, we have at least about 20 glaciers across the Arctic with which to study what is the status of these smaller glaciers north of 55 degrees. And the way that a lot of those measurements are made is this low-tech metal stake in the ice, and you go there with a ruler and you measure how much ice is gone after a period of time. Or you go there at the end of the winter and you dig a snow pit and you measure how much water was deposited in the winter. it's a kind of a counting exercise. And so those 20 plus glaciers collectively show this climate signal where they're relatively stable until the mid 90s, and then they kind of take off. And this has been attributed to a complex set of reduced global dimming due to cleanup of less sulfate. Actually, you get this brightening effect, and so that starts to kick in the 90s, as does the mounting greenhouse gas concentrations, which are heating this system. You also have the Mount Pinatubo eruption in 1992, which cooled this region, and that kind of prevented that. So then the sulfate brightening that happens after that allows the enhanced greenhouse effect to kick in, and that steeper trajectory seems likely to continue. A Greenland reconstruction comes out with a similar rate of mass loss. Adding up 5 tons per square meter, 10 tons per square meter, 15 tons per square meter across all of Greenland and all of the Arctic glaciers. That's just the average rate, and how that's added up to about this much sea level contribution in this period. But this, I guess I'm making it seem small when I do that. Thermal expansion doubles that amount, and then what we expect is an exponential rise. So with this amount, say, doubling each 20, 30 years, by end of century, we end up with more than a meter of global sea level rise. This takes us back to 1840, those same lines which you see here. I reconstructed Greenland's mass balance back to 1840, and so this accumulation of some 40 millimeters of sea level contribution, it's actually 9,000 cubic kilometers of water. Now that sounds bigger than this does. The oceans are just so vast that 9,000 cubic kilometers of loss of ice from Greenland since 1840. If you put that into the cold blob in the south of Iceland, it would be an area of 150 kilometers on a side and just 2 meters deep. So it's the right kind of scale, and we published a study that attributed about 2/3 of the cold blob appearing south of Iceland to the accumulation of fresh water in the North Atlantic from Greenland and Canadian Arctic ice melting. How could it accumulate over so much time? Is because the Gulf Stream blocks fresh water from circulating to the south. But it's not to say that it's the only thing going on, but this is a risk factor for the weather conditions in northwestern Europe. So with Greenland being about 6/10 of the Arctic land ice contribution, this AMAP SWIPO report will again present is this first kind of complete inventory, this baseline with which to gauge regional contributions. And finally, we get into projections. And we did this to ask the question, what is the significance of the Paris Agreement? What will it accomplish versus business as usual? That's the big question that I think comes from a meeting like this. How effective would the Paris Agreement be if implemented fully? And it really depends on when. There's actually no difference between now and 2030. We've effectively locked in that climate no matter what we do. The big difference comes later in the century when these bars start jumping up. And you may notice that just from 2030 on the left side, like the orange bar, that's 2030 in business as usual. And then the red bar is 2080 in business as usual. So you get this jump. And that's this nonlinear exponential rise that we have a hard time thinking about because our species thinks linearly. It's hard to think about doubling times and exponential growth, but we can confidently make a projection that after mid-century, when my kids are starting to get to my age, they should see approaching centimeter per year sea level rise. We won't see it so much. It's our kids and their kids, and so we can see this now. Now's a good time to manage this crisis, I would say. A longer view, it's interesting to look at the last 20,000 years and see how stable sea level is during the Holocene. This is a period in which civilization developed. We had a stable, predictable sea level. We wouldn't have the same civilization if we had to always move our docks around where we were parking our boats. We could, in Christianshavn in Copenhagen, that coastal infrastructure was built 450 years ago, and it's still effective today because of that stable sea level rise. What we face going forward is a commitment to a rather large sea level rise, and I put Nyhavn in Copenhagen. Many of you know this place, but any coastal place faces, as we get beyond mid-century, a catastrophic threat to coastal infrastructure, and that sea level rise, abrupt sea level rise, has begun. These are observations from a high-quality site along the United States coast, and I think it even though we get blitzed by so much other news in this world, like the news of was it this week? This U.S. presidential election, big news kind of eclipses this meeting. But in just a few weeks before that, the New York Times proclaims, really for the first time, that flooding from sea level rise is already an issue, one of the many that we have to contend with. And I think as scientists that we deliver these multi-hundred-page reports, we're counting on the decision makers and the policy makers to do their job, because I think we've done our job. So, and all the people out that are watching on live stream, thanks for joining us, and be sure to talk to your decision makers, and so that we can keep the Paris Accord alive. Thanks, everyone.
So thank you, Jason. Any questions for Jason about the